Perfect. Then welcome everybody to this small presentation about robust volumetric mapping in changing environments. It is my pleasure to talk to you about today two words, or at least recent research we've been doing in this field. As mentioned many times today, the main goal is we want to have robots and other intelligent systems interact with the world. So I think you're already convinced that vision is important for that. But one thing that is different from volumetric mapping is usually that we do not care as much about where to regress where we are, but how to model the environment to interact with it. And therefore, another major difference is that we not only want to represent the surfaces nicely, but also explicitly represent free space such that a robot or a hologram can interact meaningfully with that model of the environment. So it's very much tailored towards interaction. Another main feature, I think the community has gotten very good at this over time in a single static environments, is that we want to enable the future of these technologies to operate robustly in environments that are shared with robots or other agents as humans, which are automatically subject to changes. For this, I want to give you a short overview of two of the recent works we've been doing. Some challenges we address are on the one hand side with regard to spatial issues and then also with regard to more of the temporal issues. So for the changes, there's one example if we have noise in the poses or in the measurements that state-of-the-art methods for online volumetric mapping don't perform extremely well in capturing thin surfaces and so on, and may lead to loss of, say, thin objects in the scene. And similarly, here we see we have an environment that is shared maybe with a human. You have a service robot at your home, and you observe it at two different times. At each time step, the local scene is static, but of course there's a lot of changes between the different things, and we see that state-of-the-art methods do not really deal well with this. On the one hand side, there's no semantic reasoning. A lot of objects just get merged together into a large blob. We sort of fail to capture the new position of where objects are due to previous weights, and we also cannot really keep artifacts of objects that have moved in our previous map. So we'll go through both of these methods. We recently presented approaches to this last December at 3DB, and this is going to be presented in May. So I'll briefly give an overview of these two works. So for the first work, as Pascal already mentioned in the morning, neural latent representations are an amazing new technology that gives new insight into shape representations, and we ask ourselves, can we also leverage this for robotics? In particular, can we incrementally build a map that is usable by a robot as it explores an environment? And also in that sense, can we leverage some of the geometric context that is stored in, for example, a latent representation of this entire chair here, instead of updating individual voxels at a very spatially confined level? So essentially, the main idea that we here came up with is with input point clouds can come from any sensor, can be a depth camera or a LiDAR. We follow the standard framework of we encode it into a latent space, and this is essentially our robot map. So we have a grid of very large spatial voxels. This can be a meter cube, for example, to cover this spatial context, with a latent neural code that has the information about the geometry that is captured in this space. And the main idea is, can we make the entire robot map directly operate in this latent space? Can we do the fusion of these different codes that come in directly here? We parse them then through a decoder, which gives us occupancy probability grids. So this is quite a standard representation in robotics. You can directly query at any point in the map here, but turns out grids are very nice because you can strap your favorite robotics application for path planning or whatnot directly onto the system, and it works as usual, or you can run marching cubes to get a nice mesh. So for a short overview of the system, the idea is we decouple the spatial representation from the fusion task, so any spatial representation option works. Here we follow a state-of-the-art method, convolutional occupancy networks, where we take input point clouds, encode them through a point net encoder into more grid-based representation, and to do a classical encoder into a latent code. So this compression 3D neural network, with the main difference that we don't have skip connections because the latent code should be independent at the decoder time to the encoder time. For the encoder, where a decoder, very similar story. We again upsample everything except for the skip connections, and then it can do trilinear interpolation and have a decoder network that then gives you the final occupancy probability for your point of space in interest. And now the main issue we tried to address with this work is you have inputs coming continuously in over time. We assume you have a good state estimate, you map it to 3D or your map space, encode it into a latent code, and now we need to somehow spatially, temporally aggregate them over time, store them in the map, and have good representation. And what we here found works very well is just using a quite simple mean operation, which also has like a constant memory footprint in the map. This has also worked well for other works that were done more or less at the same time. And then we actually have a fusion network that takes this mean. And it is not actually fusion, it's more a remapping network between, we have this running mean fusion, which takes all these codes, and typically the latent space is not a Euclidean space. So just taking the mean of the codes doesn't give you the mean of the representation. But apparently it contains a lot of information that can be leveraged by a network on which components of the network were important for this. And then the main idea here is as the supervision signal, or we can feed it to a decoder and get what we care about. The supervision signal is, we look at the post-hoc effect. So if you got all measurements that you are going to take for this voxel, you combine them together and feed them jointly through the encoder-decoder, which gives you essentially an optimized representation of all your input data. It gives you a latent code and the output. And here the encoder and decoder is frozen. You can take your favorite spatial representation network. And then we add 2 losses, essentially on the output, because we want to have the same output as the one you would get from your final representation. But it turns out also by constraining the latent space, this can actually work well. And we did train this all on synthetic data, or the spatial representation is trained on synthetic data, and then the fusion is trained on real-world data, but without the addition of noise. And then we add noise to the poses with different magnitudes, and this is essentially what our test data looks like. And we observe exactly these effects, that as the noise gets bigger in classical representations, thin surfaces cannot be captured as well, and they tend to not be well represented in your map, whereas our method has some thickening artifacts due to the noise, but the important part for robotics is you actually capture these objects in your map, because you don't want to navigate into these if you're a drone or something like. We can see this a bit better if we visualize it by error. So many of these objects that have a peculiar geometry are not well captured, and also the general error seems to be higher. We can see this in the numbers. Don't look too much at them. The main takeaway message is in terms of accuracy, we actually are on the same level. It doesn't really matter. But the key point that we are interested in from a robustness perspective is the objects that are there in the real scene are much better captured with our fusion method compared to a classical approach, up to twice as much if we exclude the ground. So a short summary of this, we presented a network that, or a method that can operate on, create a robot, a volumetric map based on neural implicit representations. We can incrementally fuse data of some of these representations. And this was all trained without any noise and actually deals pretty well. It also works well with sparsity if you only feed it 5% of points. And the nice part is we care about robots that operate on this, so you can run this at interactive rates, overall about 3 frames per second. On a CPU only, it's much faster on a GPU. So this is something we can strap onto our drones. Then for the second piece of work, which is more about the long-term changes, is again the figures I had from the beginning. And the main motivation for this piece of work is that typically the world does not change at random, but in a semantically consistent way. So here we look at, you don't have single voxels that change, but usually maybe your sofa is rearranged or something like. And the main question we answer here is, can we leverage this high-level information and the semantic consistency to do incremental online mapping in a changed scene that is semantically and temporally consistent? So for this, we essentially propose a hierarchical map representation where we say we want to reason about things on the level of objects. So we model the scene as a sparse collection of objects, but of course every object has a spatial representation, its extent, its geometry. And there's a lot of computational tricks as well to make it hierarchical and fast. And then the main idea is we only integrate new data into things that we can track between frames, also in a semantic way. So this way we guarantee that we only modify surface representations that are semantically and temporally consistent. And then we do all the reasoning on this set of locally, semantically, and temporally consistent patches, which hopefully gives us better results than doing the reasoning on the level of voxels, which was the case before. So there's a short video of how the approach approximately works. We incrementally build a map of the environment. And we see here that we have the different submaps for the different semantically consistent things in the world. And what is particularly important here, because we want to get a volumetric map of the entire environment, we care about the objects and the background and the free space, everything that together gives you the full volumetric representation and not only sparse representation. And together, you get a nice volumetric map. And here, again, this is the second part of the pipeline. Essentially, you run your favorite panoptic segmentation framework. We do tracking based on instances for the foreground and semantics for the background. There's some implementation details on this. And the main point is that we really only modify things that we can locally make sure are consistent, which is shown in solid. And the past measurements, these patches are shown in shaded. And here we see more as the spatial reasoning, so we can compute intersections between these surfaces, and we actually see here in solid green we have what the robot currently observes, and then there's previous patches that actually do agree with our measurements, so we are certain they are still here, and then there's some patches that don't agree with our measurements, so you throw away the entire patch and don't merge them together. And for the parts that do fit well, you can merge them together and do all sorts of processing to get the more compact representation. And the outcome of this is that on the one hand side, it's very naturally multi-resolution because each object can be reconstructed in its own scene. So we see here like more details on the cups that you usually would not have in a robotic environment. We know a wall is not an interesting feature, so we can reconstruct it at a low resolution. And what's particularly important, you get this spatial temporal query directly from one map when you move through it with a robot. So we have here some data visualized as a slide in solid that the robot has observed to be free or occupied, so you know you can or cannot go there. But what is nice, we have these patches from prior observations that were incrementally built. So here we have a good idea of what the world is expected to look like, but we know or don't know for sure whether it will look like for this, so you can use it for planning, but maybe don't fly into it. And we can also leverage the semantic consistency. For example, the last time we observed a table, it extended to here. And since this part of the table is consistent, we also expect these parts to be occupied due to the semantic consistency, which is information that you can leverage. In terms of the multi-resolution, here we see some numbers where blue is hours and there's some baseline. And the important takeaway message is here in black, we see also a multi-resolution approach that is based on just the sensing. So if you observe something in high resolution, then you can reconstruct it in high resolution, so it's lacking all the understanding and semantics part. And we can show that if you know something is a wall, for example, you don't need to reconstruct it at a high resolution, even if you observe it at a high resolution, and you get about the same reconstruction performance with 20 times less memory footprint. And here, in terms of the online performance for the temporal reconstruction, where you can see, so this is data collected on the second day. You have a previous observation of your environment, and here you do the online temporally consistent mapping, essentially. And first, what we observe here, our method in blue, in terms of reconstruction error, has the same quality as if you would start completely from scratch. So you get the same accuracy compared to not having any prior data. But if you look at the coverage of the environment by reusing the previous measurements that we are confident are in agreement with our covenant data, you get a much quicker increase in coverage. And also here, you end up having a more complete map because you can leverage data that you maybe did not observe during the second run. Same here, the baseline methods in green and black are not able to remove all of the artifacts from your map, so there remains a final gap in terms of performance. Lastly, you can engineer this quite nicely with a hierarchical way and a bit of parallelization. Actually, it turns out you can run this at reasonable frame rates. In particular, this is on real data. There's a bit smaller camera resolution. And with the real segmentation, you don't see as many objects that you capture. But then you can run it at up to 30 hertz while doing all the online change detection. So to briefly wrap up this work, the main idea is we have a hierarchical map representation based on semantically and temporally consistent submaps. And one thing that's important, even with very poor semantic segmentation, you get good spatial reconstruction. Maybe if you look here at a solid is ground truth, and dashed is we take intentionally a network off the shelf without refinements that gives somewhat poor performance. And in terms of the spatial representation of the surfaces, it works quite well. And again, the main takeaway message is don't reason at the level of individual pixels or voxels, but semantically consistent objects makes life easier. And we demonstrated a system that can actually be used by a robot. So to briefly summarize what I presented in this talk is learning-based methods show very high potential for surface representation and the semantics and understanding the scene. I think we've come a great way, but I don't think we are yet effectively there where you can represent a changing and dynamic and complex environment to the degree we would want it to. And then again, sort of this hierarchical approach, I think the way to tackle this is by combining low-level geometry representation and shape priors there together with more high-level extractions and actually understanding of your scene and what you want to model. A short outlook, based on what I already said, we plan or currently actually have projects that do combine these things into more spatially robust and temporally robust frameworks, both from the learned representation side and from a more classical inference side. And then, because robots are embodied, they can actually choose to move in a way to get a better model of their environment, which is active perception. And there we recently submitted 2 papers. These are the preprints for how a robot can move to observe the geometry of an unknown environment, or how you can autonomously improve a semantic segmentation model by taking smart observations. So if you're interested in that part, then please talk to me during the break. And with this, I'm happy to take some questions.
Okay, do we have any questions?
Thanks. I'm just curious, as you have semantic segmentation of the objects, can you utilize maybe the probability that the chair will most likely be moved constantly, like depending on the object type, or some bag is dropped and most likely in the next observation it won't be there or will be shifted, and while some objects like, I don't know, TV table or something like that is very unlikely to be moved. Do you think would that help to improve, or is it possible to incorporate this info?
It is totally possible to incorporate. Once you have this sort of abstract representation, it's a lot easier to do reasoning on that level. And we actually have ongoing projects that try to predict changes of scenes based on these abstract representations. And there's very promising work that was very recently released that suggests, actually, if you look on the higher level understanding, you can model, say, semantic relations between objects in scene graphs. And if you do this in a smart way and have a good scene graph or a graph neural network, you can actually predict those changes or the most likely places for object based on only the abstract representation. So we're actually working on also getting this incorporated into a mapping system.
Cool, very interesting.
But thanks for that question. It's a great question.
Okay, any other questions? So if not, we will have a break now, and I think we continue at 3:20 with the last session.
Thanks.